So I welcome all the participants back to our second session of today's ATAL FDP. The guest speaker we have now with us is Dr. Raja from Government College of Engineering, Salem. He completed his BE at Government College of Engineering, Salem in the year 1999. He then completed his MTech at NIT Trichy and further pursued his PhD at Anna University, Chennai. Coming to his working experience, he was employed as a lecturer at AMS Engineering College for a period of 6 years, after which he moved on to the manufacturing sector as a section engineer in the Southern Railways. Furthermore, he has then joined Government College of Engineering, Salem, and he has been associated with the college for the past 11 years. In a total, Professor Raja has a teaching experience of more than 20 years, and he has more than 15 publications in reputed ACI index journals with high impact factors, out of which major of them focuses on nanofluids. So we are expecting a very good session from you, sir. I kindly invite you to handle the session. Thank you very much. You can proceed with the session now, sir.
Okay, thank you, Sachin, for your nice introduction. First of all, I would like to thank the management of Gnanamani College of Engineering and funding agency AICDD for giving me this opportunity to participate in this workshop, the today's workshop. And I also congratulate the coordinator, Sachin, and other faculty members, those who are involved in the seminar, to be a great success. So with these few words, I would like to start my session. First topic is given to me is X-ray diffraction, or it's sometimes called as X-ray diffraction and X-ray crystallography. See, X-ray diffractions or diffractions are otherwise called as X-ray crystallography. Why it is being called as X-ray crystallography? Because it is meant only for crystalline structure. The materials which has crystalline structures can only be used to the X-ray diffraction. That is what is being called as X-ray crystallography. And this X-ray diffraction is a very vital tool for examining the microstructure, molecular structure, atomic structure, and phase and other components present in the particular compounds. It is plays a very vital role in characterization, analyze and interpretations of the substances, and particularly in so what you call it as a composite. So nowadays, most of the peoples are doing research in composite. The characterization of composite is very important. So with for that characterization, the XRD technique is very important, useful technique, right? So first, what is XRD? So XRD is a technique which is used to study the microstructure and atomic structure of crystals using X-ray diffraction. So again, I'm repeating, it is used to study the microstructure and atomic structures of a crystal. It is not useful for amorphous. If a substance is amorphous, it cannot be utilized, it cannot be used. It is only applicable for crystals, right? So it is also used and to measure the presence, quantity, and the phase of minerals in the sample. Your samples may have a number of minerals. You may incorporate number of minerals to acquire some property, desired property. How it present in the substance, how it present in the sample, how much quantity is present, what is the phase of the minerals available in the particular sample. Those things can be characterized, can be measured with the help of XRD. These are the objective of having XRD. So now we know what is XRD and what is X-ray. Why we talk about X-ray here? Because it is a X-ray diffraction. From the name itself, we can understand the ray which is used for characterization of the substance, or you call it as a sample, is X-ray. Why Also, or what is an X-ray? X-ray is an electromagnetic wave of small wavelength and high energy. It's a light wave. So light wave having the small wavelength and high energy, very high energy. So, okay, what is the wavelength? It is roughly approximately around 0.5 to 2.5 angstrom. The wavelength of X-ray is around 0.5 to 2.5 angstrom. Right. So why the X-ray is selected for this study, for a diffraction study, to get the diffraction pattern? Why don't see here? The interatomic spacing is around 2 to 3 angstrom for all crystals, whereas the wavelength of X-ray is 0.5 to 2.5 angstrom. So both are almost same, right? So that the X-ray is used to analyze the atomic structure or molecular structure and other things of a crystal. The condition is the wavelengths should be equal to the interatomic distance or grating distance of the substance. That's supposed to be so that X-ray is suitable for the study of atomic structure of a sample. Right. So this is the justification. So what we discussed so far is what is XRD? XRD is a technique which is used to study the microstructure and atomic structures of the crystals with the help of X-ray diffraction. Right. And why X-ray is used? What is X-ray? X-ray is a small wavelength. It's an electromagnetic wave of small wavelength and high energy. It has a high energy. The what's the wavelength? It is in the range of 0.5 to 2.5 angstrom. So why it is suitable? Since the atomic distance, interatomic distance, is almost equal to the wavelength of the X-ray. That is why it can be studied. Because if the interatomic spacing and the wavelength supposed to be one and same, so that it can be diffracted. So if an electromagnetic wave is to be diffracted, then this condition should be satisfied. What condition? The atomic distance, interatomic distance should be equal to the wavelength. Right. So before going to the next one, so we know how the X-ray is generated. X-ray is generated with help of target metal. So target metal may be a molybdenum, copper, cobalt, iron, or chromium. Right. And electron is used to hit the target metal, and the target metal releases X-rays. So X-rays, what's the amplitude of X-rays? Sorry, the wavelength of X-ray is given as 0.71 for molybdenum, copper 1.54, and so on. Chromium 2.29. So it starts from 0.71 to 2.29 is the wavelength. So it is more suitable for analyzing microstructure. Right. So here you can see here the electromagnetic spectrum. See the wavelength, the first one is a wavelength. It starts from 10 power 3 to 10 power minus 10. So 10 power minus 10. 1 into 10 power minus 10 meter nothing but equal to angstrom. So 1 angstrom. So plus or minus 1 angstrom. The wavelength of, see, I am searching my cursor. See here. So this is what? X-ray. The X-ray range, the wavelength is plus or minus 1 into 10 power minus 10 meter, which is angstrom. So around what we said is 0.5 to 2.5 angstrom. See in the other side, so we can see frequency. Frequency is higher frequency. It is in the range of 10 power 18. We know the pressure volume relationship. Pressure and the volume is inversely proportional at a constant temperature. Similarly here, so we know the wavelength and the frequency is inversely proportional. So when the wavelength is increasing, wavelength is decreasing, the frequencies get increased. See here, see the wavelength is 10 power 3, frequency is 10 power 6. Whereas wavelength is 10 power minus 10, frequency is 10 power 18. So the frequency is getting increased when the wavelength is being decreased. So at the high frequency, it is automatically possesses the high energy. So this is the reasons to justify X-ray as the suitable medium for inspecting samples to study the microstructure. Right. I hope you understand. Right. So what's the principle? Okay. So we discussed so far what is XRD and why X-ray is meant or used here for inspection of a sample to understand the microstructure and other thing. Then what is the principle? So it is based on the principle of constructive and destructive interference of monochromatic X-ray on crystal. What's a constructive and a destructive interference? So particularly here, so we use the constructive interference. The diffraction occurs when it is scattered by a periodic array with a long range order producing constructive interference at a specific angles. See, this constructive and destructive interferences that we will discuss further, right, when we go on. So I will discuss again and again so many times, so I don't want to touch it now. Right. So what is the diffractions here? Here what we used, though we have constructive and destructive. Once you have constructive interference, you always you must have a destructive interference. But here the dominating one is the constructive interference. See, the diffraction occurs when the X-ray is scattered by a periodic array with a long range order. So we know the crystal structure. The crystal is made of, see how the crystal is made. So it's made of cubicles, right? Just like a building block, the basic cell, unit cell, then number of unit cells will form a crystals, right? So that unit cells have some uniformly repeating order, right? So that X-ray is diffracted or scattered by the periodic array with a long range order. It's producing constructive interferences at specific angle. It is not always, it is at a specific angle it gives the constructive interferences. Let us assume, so I'll show. See here, see, let us have this atoms. So here atoms or number of atoms are arranged in a regular pattern, right? See, when you hit an X-ray in a horizontal direction, so it will hit and it will energize and it will dissipate here, right? There is no constructive interference. It will be dissipated. There is no constructive interference, only destructive interference will be there. But at a particular angle, if it is in this angle, so you will be getting a constructive interference. You will not be getting the constructive interferences always, but at particular angle you will be getting it. Particular sections will be getting it. Right? That's the point I want to emphasize here. So the diffraction occurs when it is scattered by periodic array with a long range order, producing constructive interferences at specific angles. Right. So we are getting when you hit the X-ray on electrons, the electron scatter or the electron diffract the X-rays at a particular time. The reflected or diffracted rays, if it is constructive in nature, you will be getting the X-ray. Right. So the electrons in an atom coherently carrying. Generally, the electrons in an atom coherently scatter light. The strength with which an atom scatter light is proportional to the number of electrons around the. What is the strength of reflected X-rays? It depends upon the number of electrons present around the atom. That is very important. So based on that, the strength of the what we call the spectrum. It depends. Right? Once you get more spectrum, then you can understand that number of electrons are more nearby. Right. The atom in the crystals are arranged in a periodic array and thus can refract light. Yeah. So why we chose crystal? In crystal it is arranged in a periodic array, and that's why it can diffract light. If it is amorphous, it cannot diffract. Because there is no periodic array, it is randomly arranged. In amorphous, it is randomly arranged, so it cannot be. The scattering of X-ray from atoms produces a diffraction pattern which contains information about the atomic arrangements within the crystal. Yeah. So once, as we said earlier, at a particular angle, if you scatter incident X-ray, which will give you a particular pattern, diffraction pattern. That pattern is telling you the atomic arrangement, because already we told you that the strength of the spectrum, it depends upon the number of electrons present there. So the scattering of X-ray from the atom produces a diffraction pattern which contains information about the atomic arrangements within the cell. So how it is diffracted, the pattern, how the pattern look like. Based on the pattern shape, we can understand how the atomic arrangements there in the particular crystal. The angle and the intensity depends on the arrangement of atoms in the sample. The angle of reflection and the intensity depends upon the arrangement of atoms and number of atoms, of course. So amorphous materials like glass do not have periodic arrays with a long range order, so they do not produce a diffraction pattern. Yes, this we told, this we discussed. So amorphous is not suitable for X-ray crystallography because it is not having a periodic regular array, right? But what actually present in general, the 95% of all solid materials can be described in a crystalline form. Almost all the materials are having the crystalline structure. When X-ray interacts with the crystalline substance, one gets diffraction pattern. Yes. So of course, don't worry, because so the amorphous material is very less only. So we are having most of the materials in crystalline structure, so that it is no issue. When X-ray interacts with the crystalline substance, it gets diffracted. It gets diffraction pattern or diffracted. Right. Okay. So let it be. What's the use? Mass. Right. Yeah. That's the use. It is defined by Hull in 1909, and he said every crystalline substance gives a pattern. Yeah, every crystalline substance gives it. Sir, you're repeating the same thing, sir. Yes, of course. But the same substance always gives the same pattern. That is very important. The same substance always gives the same pattern. Yeah, just like your fingerprint. So whenever you measure, your fingerprint won't change. Your face may change, but your fingerprint may not change. Just like that, the crystalline, every crystalline substance is a pattern, but that pattern is unique in nature. It is unique in nature, just like our fingerprint. And in a mixer of substance, each produces its pattern independently of its test. If it is a mixer, if it is a single crystal, then no, there is no issue to give a pattern that is unique in nature. But if it is a mixer, then it produces a pattern independently of others, right? So each crystal produces independently. Each crystal produces its own pattern. The result will be the combined one. That's different. Hence, the X-ray diffraction pattern of the pure substance is therefore like the fingerprint of a substance. Yes, of course. The powder diffraction method is best idea used for characterization and identification of polycrystalline pieces. Right. Okay. See, so we said it is like a fingerprint. So what's the use of fingerprint, sir? Yeah. So nowadays, if you have your if you give your fingerprint, so one can get every data about you, because in Aadhaar, so we linked our fingerprint, right? So once if you anybody knows your fingerprint, then one can understand what is your name, address, age, locations, etc., what is your PAN number, right? Everything can be obtained with the help of your fingerprint. Similarly here, if you have the diffraction pattern of the blue substance, you can give the entire detail of the particular substance. Start from the phase, what is the structure, what is the quantity, how much it is present, and everything can be given with the help of the diffraction pattern. Right? Right. So what's the user? Okay, it is given. No problem. Then, yeah. See, there is a organization, JCPDS, Joint Committee for Powder Diffraction Standard. So that organization collected the fingerprints of, the diffraction pattern of almost all inorganic and organic components. About more than 50,000 inorganic and 25,000 organic compounds. Diffraction patterns, what you call it as right? Just like our fingerprints, they collected and they have in a form of soft copy. So what is the use? So we are having our own material or substance. We are testing with the XRD machine. It gives us some diffraction pattern. See, that diffraction pattern can be compared with the available database given by the JCPDS. So JCPDS having the store, right? Like a store, they are having a resource. So if the pattern like this, then it is supposed to be this space. If the pattern like this, it is supposed to be this material. The pattern like this is supposed to be in this structure. So like that, they give all the data. That data can be compared with the tested refraction pattern and the particular characterization of the sample can be done. Furthermore, the area under the peak are related to the amount of each phase present in the sample. Yeah. Just like in our PV diagram, the area under PV diagram gives you the work done detail. Similarly here, the peak, the peak, area under the peak are related to the amount of each phase present in the sample, right? So that can be calculated, right? So this is the XRD pattern of SiO2. The SiO2 is same chemical composition, but it is in the three different form: glass, quartz, cristobalite. See here, the cristobalite and the quartz are in a crystalline structure, whereas glass is in amorphous structure. That we know. Glass is amorphous. So, as we said already, the XRD can be used for the crystalline material only. So, see here, this red diffraction pattern gives about the cristobalite, and there is a blue gives the quartz. So, what sir, here also it is giving some graph, yes, it is giving, but it has no sharp peaks. It has sharp peak. If it has sharp peak, then it can be identified. If it has like this curve, then this is not useful. This we cannot do anything with this curve. So, but one you can understand that once if the curve like this, then you can understand this is amorphous. If you have the peak like this, then you can understand this are the crystalline structure. Whether it is a crystalline or amorphous, that you can understand from this curve. So though the material is same, the chemical composition is same, but the XRD pattern for these three are different. So from this pattern, we can understand whether it is whether the tested sample is the cristobalite or quartz or glass. That can be observed. Right. So this is about the XRD spectra. What you call it as XRD spectra or extra diffraction pattern. Either you can say. Right. So we know this XRD is useful for crystalline material only. So how the crystalline material is characterized? It is characterized by the long order periodic arrangements of atoms. So that we know this is the basic of material science. Atoms are arranged in a regular pattern, and that is the smallest volume element that by repetition in 3 dimensions describes the crystal. This smallest volume element is called unit cell. What's a unit cell? This we might have studied in the material science. We know when you construct a wall and when you construct a building, it is constructed with the help of brick. So a number of bricks arranged in a systematic way, which form a particular construction. The basic unit is a brick. That brick is what we call it as a unit cell, the building block of the particular crystallite. Right. See, if it is a unit cell, it must have a 3 dimension like ABC, and the angle between these 3 axes ABC called alpha, beta, and gamma. Right. These crystal structures are termed given in terms of previous lattices. That is given in the table. This is not much important here, but you must know. So based on the crystal structure, the XRD pattern will be different. Right? Right. Again, further, initially I told you So we'll discuss further about the destructive and constructive interference. Now we'll discuss it. See, we know an electron in alternating electromagnetic field will oscillate with the same frequency as the field. Yes, an electron in the alternating electromagnetic field is oscillating. When the X-ray beam hits an atom, the electrons around the atom starts oscillating with the same frequency as X-ray. Right? The electrons get vibrations, or it starts oscillating as in the case of X-ray. Right. So it starts oscillating. Right. In almost all directions, we will have the destructive interferences. That is, the combining wave are out of phase, and there is no resultant energy leaving the solid sample. Right. When the X-ray hit the atoms, that is vibrating and it is giving some refracted wave or deflected wave, what you call it as, right? But the resultant waves are out of phase and there is no energy, resultant energy is leaving the solid sample. There is a complete destructive interference. What is the destructive interference? If the two or more waves are coming or superimposed, so the start and end points are one and same. But if this phase is opposite or the phase is 180-degree lagging or leading, so what happened? The amplitude will be opposite in direction. So what happened? There will be no resultant energy will be given. That is what destructive interference. Whereas in the constructive interference, if the two or more waves are superimposed and the starting and end points are one and same, and there is no phase difference, then there will be a constructive interference. The amplitude will be the amplitude of the particular wave can be improved or increased. Right. So now we call it as a in phase. If there is a constructive interference, that we can be said as a in phase. If it is destructive interference, it can be said as a out of phase. Right. Since the diffracted beam may be described as a beam composed of a large number of scattered rays mutually reinforcing one another. Yes. Hence, if a diffracted beam may be described as a beam composed of a large number of scattered rays, so mutually reinforcing one another. Right. So this model is so complex, right? Because it's handled mathematically, it's very complex. And so we have some parallel planes, some planes to describe the pattern, what's the diffraction pattern in the constructive manner. See, the orientation and interplanar spacing of these planes are defined by the three integers H, K, L or indices. So we have H, K, L indices, so which gives the orientation and interplanar spacing of these planes. This is what we call as H, K, L. At a given set of planes with the indices H, K, L, cut the axis A, cut A axis of the unit cell in H section, whereas a B in a K section, C in a L section. The 0 indicates that the planes are parallel to corresponding axis. So we already discussed, see, when the X-ray hits the electron at particular axis, only it will give the constructive interference. Right? So that plane can be identified with the help of HKL. HKL, what is HKL indices? If it is H, so it cut the unit cell in H section. B, the K means it cut the B axis in B section and the C axis in L section. Right? So it may be a little confusing, but when I give the example, it will be easy for you. So example 220 plan, for example, let us take 220, HKL is, H is 2, K is 2, L is 0. 220 plan cut A and B axis in half, but are parallel to C axis, right? So there is a 220 plane. If the axis incident ray it's passed through 220 plane, then it means it cut A into 2, B into 2, whereas C in the axis is parallel, right? See, I can give the illustrative example. This will be useful to understand if we see it. Right. See here. So 100. What is 100? So 100 means, see, it can cut axis A at one location, right? And other two locations, other two axes B and C are parallel. See this hatching can cut A, but it cannot cut B and C, right? See, come to this point 20. If 200, it cut A axis into two, right? Whereas it cannot cut in B and C. B and C axes are parallel. Similarly, see here 110. 110 means this plane cuts A axis and B axis, whereas C axis is parallel. See this cutting plane, this is parallel to C, whereas it can cut at one locations A and B, right? See, you might have studied in engineering graphics. If you are all belongs to mechanical engineering, you might have studied engineering graphics where you might have studied section plane, right? Similar concept here, right? So if it is 200, it cut into two the particular A axis, but other two axes are parallel. For example, 300, what is the meaning of 300? 300 means it can cut the A axis into three, whereas B and C are parallel. Hope you understand, right? See another example given here, the 200 plan of atoms in NaCl, right? NaCl, see here, 200. 200 means it can cut into two half, right? See, this is the structure, right? The crystal structure unit cell. So cut into two, right? So two half, but it can cut only one axis. This axis only it can cut. So, but other two axes it is parallel. For this axis and for this axis, it is parallel. For axis, it can cut only the axis A. It is parallel to axis B and C. Similarly, here you can see 220 planes for NaCl. 220 means what? It can cut into two. The axis can be cut into two. A and B axis both can be cut into two, where C axis is parallel. Where the C axis, see here, this axis C, the C axis is parallel to this plane, whereas other two axes can be cut. So this is what the sections, so you might know, see at different angles, the incident ray may be penetrates or interfere the molecules or atoms, so that we can get the diffraction pattern. That a different angle or that orientations can be given in terms of this indices, HKL indices. HKL indices may be 100, 200, anything it may be, right? Right. So next, so let us see here. So this is what in the arrangements of atoms in the unit cell, arrangements of atoms. See, there is an incident X-ray 1 with a wavelength lambda. It comes and hit the atom and it's getting reflected here. See, the angle of incidence theta, the angle of reflection is also supposed to be theta. The theta is nothing but the angle between the incident ray or a reflected ray with the surface. Whereas the angle between the point of incidence and the point of diffraction is 2 theta. The angle between the angle of incidence or the point of incidence and the line of diffraction is 2 theta. Right? See, you may remember the wavelength is supposed to be equal to the interatomic spacing, that D space. This D space supposed to be equal to the lambda. This is what we discussed very first, so that it can be. That is why the X-ray is suitable for this study, the X-ray diffraction study, the crystal structure study. Right? See, you must understand that D spacing, this D spacing must be equal to lambda. See here, this d spacing is equal to lambda, right? Right. And this is what? Half lambda. See, this is a second ray mm, which pass through the second atoms and get reflected. See here, there is an optical path difference. See, and this ray just travel this much distance, whereas the second ray travel a little more distance, which is equal to, this is what lambda and this is what lambda. Okay, this is 2 lambda, and you can consider this as a right angle triangle if it is a right angle triangle, and if this is theta and this supposed to be theta. If this is theta, then we can say opposite side by hypotenuse. Hypotenuse is a DHKL, and whereas this one is what? Lambda by 2. So sin theta is equal to lambda by 2 divided by DHKL. And here, this side also you will be having the same thing, because there are two right angle triangle. So here also you will be having the same value. So what is the distance? This distance can be found. Opposite side is nothing but lambda by 2, that is equal to DHL sin theta. So lambda by 2 plus lambda by 2, that is equal to 2d sin theta. So you may understand that. So lambda by 2 is equal to DHL sin theta. So here lambda by 2 is equal to DHL sin theta. Then if you rearrange, you can get n lambda is equal to 2d sin theta. This is what we call as a Bragg's law. So the Bragg's law is important. So what's the Bragg's law say? See, for XRD, this lambda is fixed. The lambda is fixed because we know the wavelength of the particular X-ray. And see, I'm getting the cursor. See the d spacing and sin theta. D spacing, if the d spacing in sin theta is inversely proportional. It is, since it is fixed, the d spacing and sin theta is fixed. If theta is fixed, the d spacing is very important. For parallel planes of atoms in the space DHL between the planes, constructive interference only occurs when Bragg's law satisfied. When Bragg's law satisfied, you will be getting only constructive interference. What is the Bragg's law? N lambda is equal to 2d sin theta. It's supposed to be the lambda. It's supposed to be 2d in sin theta. If the distance DHL is should be the d is supposed to be lambda divided by 2 sin theta. If the distance is that much, then you will be getting only the constructive interference. Or in other words, I can say, to get the constructive interference, you must satisfy Bragg's law. Bragg's law say that n lambda equal to 2d sin theta. That's important. Right. So this is some more illustration which will explain the Bragg's law. Right. The same thing, right? So this is waves coming and reflecting. So some things I don't want to repeat. So this will get right. So with this knowledge, so we'll come to the XRD spectra. What is the XRD spectra? XRD spectra is nothing but the diffraction pattern, otherwise named as XRD spectra. See, there is a goniometer. Goniometer is a part of XRD, which constitute of X-ray tube, sample holder, and sample in the detector. Right. So this is what's the goniometer assembly. So here the X-ray tube, so we know which is emitting the X-rays. That X-rays fall on the sample, and the reflected rays, X-rays, will be detected by the detector. This is the simple assembly, right? The sample is placed over the sample holder here, and the X-ray hit the sample. So yeah, when the X-rays hit the sample, and the diffracted pattern is identified by the detector. So this is the idea. The detected diffraction is this one for Fe3O4 and this one for Fe2O3. Right. So what it is? See, these are the indices 2 to 0 at the plane 2 to 0 the peak is observed. At 311, this peak is observed. 222, this peak is observed. Right? See, here the 2 theta angle. See, for what 2 theta, what is the intensity? How much X-ray diffraction is obtained? See, at 20 degree, the 2 theta angle is 20 degree. There is no peak. There is only smaller peak is there. But at see, let us assume this is a 25 degree. There is a peak. At 25 degree, the plane is 211. You will be getting this peak. Right. So how it is obtained? The sample is placed on the holder. Right. The sample is placed on the holder, and see, the sample is rotated with the speed of theta, whereas the detector will rotate in the speed of 2 theta, so that the focal point cannot be changed. Then you can get the perfect focus, so it can detect the X-ray pattern. Right. So you please try to understand, the sample is rotating with the speed of theta, whereas the detector is rotating in terms of 2 theta. So this is what we call theta and 2 theta spectrometer, XRD, right? Right. So while doing like this, we will be getting the spectra. The data is plotted here. Say x-axis we have taken the 2 theta value, where in the y-axis the intensity is taken. The intensity unit is AU, the arbitrary unit, or it may be given in terms of counts, number of occurrences that is given. Right? See, this is what the sample of XRD spectra obtained for a sample material Fe3O4. Right, and I can see the explanation. And X-ray diffraction pattern is the plot of intensity of X-rays scattered at different angles with sample. Yeah. X-ray diffraction pattern or X-ray spectra is nothing but a plot between the intensity and the 2 theta angle. Right? So this is the plot between intensity at 2 theta angle at different section plane, different angles. Different angles means the different 2 theta angle. Right. The detector moves in a circle around a sample. Yeah, it can move in the circle around a sample. The detector position is recorded as a angle 2 theta. Right. The detector records the number of X-ray observed at each angle 2 theta. So this unit detects number of occurrence of X-rays that is recorded here. See, here it may be 1000 times, it may be 500 times, it may be 50 times like that. Right. The detector records the number of X-rays observed at each angle 2 theta. The X-ray intensity is usually recorded as counts or as counts per second. Right. To keep the X-ray beam properly focused, the sample will also rotate. Yes, I already told you that the sample will rotate at theta speed, whereas the detector will rotate at 2 theta speed. Right. Right. See, this is what we tested Fe3O2 and Fe3O4. See, if suppose if you take a sample and if you get a XRD spectra which exactly matches with this peaks, then you can understand that your sample have Fe2O3 or Fe3O4. Right? You have to, suppose you made a composite which includes Fe3O4 and Fe2O3. Then you have to make a sample and test with the XRD spectra. And if your spectra having so peaks as in the case as available in the picture, then you can easily say that sample contains Fe2O3 and Fe3O4. Right. Right. Now, the International Center for Diffraction Data, ICDD, or JCPDS, Joint Committee on Powder Diffraction Center. It was the former name, and the present name is International Center for Diffraction Data. They are providing the reference data. So I already told you around 50,000 inorganic and 25,000 organic crystalline samples they are having and their pattern, XRD patterns they are having, right? So that database is available in the different format, and that normally that will be supplied along with the manufacturer, right? Or you can get it direct from the JCPDS or else, right? The database contains information like d spacing, chemical formula, relative density, etc. Once if you have the XRD image, that image can be matched, search and match technique, right? It's matched with the available database. The database is provided by JCPDS, and with that, it will compare and it will say everything. What is a D-spacing, what is a chemical formula, related intensity, say everything. Alright, see this database is released every year. Every year it is updated. Any new component, any new crystalline structure is identified and discovered. Those diffraction pattern also added, and this software is released every year. And the manufacturer, it is availability, the data is customized to suit the requirement of the company or the manufacturer, so that they can easily use the data in many ways. Right. So we can take an example of a single phase crystalline, right? So how to use the XRD, or how to analyze the XRD pattern manually. That so we are not going to do manually, but so the procedure, what it is doing, that so we are discussing here, right? So you see here, this is the intensity of versus a 2 theta curve for some substance that we don't know what the substance it is, right? So first peak, second peak, third peak, and so on. The peak versus D spacing is given, right? So with this data, we have to identify what material it is. So how to do? So first, what's the procedure? First, the strongest three peaks. The first is the strongest three peaks. The D spacing are 2.82, 1.99, and 1.63 angstrom. Right. So we can search the JCPDS data bank. So from 2.84 angstrom to 2.8 angstrom. So it is observed about 17 substances approximately similar to the D spacing what we suggested, 2.82 to 1.4. But see here, the first peak is in the 2.82 angstrom. The second one is 1.9, it is okay. The third one is 1.63. See here. So, so from the 17 substances, we have taken only 4 because very closer to the value given D2, D3. And see the D3 value, the D1, D2 are almost common for all the substances, whereas D3, 1.63 is matched with it, right? So I can say this pattern is meant for NaCl. This pattern is meant for NaCl. This is the method, this is the technique, or this is the way how the computer can interpret the XRD data with available database. Right? See, and of course, again, you can see here, this is N for NaCl. N for, if you take Na alone, then that will be different spectra. Cl means it will give some different spectra. But if it is NaCl, yeah, so it has the spectra like this, right? Okay. All right. So how to interpret XRD data? So far, what we discussed is what is XRD, why X-ray is used, and what's the basic principles of XRD, and how the XRD spectra is obtained, and how the interpretation of the XRD is done, or how to identify what the substance it is. That is so far what we discussed. Now, further interpretations of XRD data, phase versus XRD. So, what's the phase of material, whether it is a crystalline phase or amorphous, or whether it's a quartz, or what's the phase? So see here, this plot. So will give you this. We already discussed, I think, right? So this plot will give you the 3 different forms of SiO2, and 2 are crystals, 1 is amorphous. So from this we can understand whether it is amorphous, 1 is amorphous, the glass is amorphous, and these 2 are crystal form, right? Right. See how we are saying, since these 2 have sharp peaks, this red and blue having the sharp peaks, so you can understand that these 2 substances having the crystalline structures, whereas the glass is having a amorphous structure, right? the diffraction pattern of the mixer. So right. So how the diffraction pattern of the mixer is uh, observed, right? See here, if you take these three, a mixer contains the coils, crystallography, and glass. If the mixer consists of these three, then the resultant XRD will be available, will be coming like this, right? So this will be the resultant if it has a mixer of these three. So from this, how can we understand? We can understand that it has amorphous phase also. In the mixer, it has amorphous also, and of course, it has a crystalline structure also, right? And so from the XRD pattern, we can determine what crystalline phase are in a mixer, right? How much of each crystalline phase in the mixer, if any amorphous material present in the mixer, these things can be studied. Right. All right. So now, how to analyze the XRD data? See the peaks. The green color is what? The peaks observed by conducting the experiments with the help of XRD machine. Right? Whereas the red lines are the peaks observed from the database provided by JCPDS. Right? Right, these two has to be compared. After taking the XRD spectra, it has to be compared with the reference. Right? See, each and every peak with the reference and the sample should be matched. So here almost matched, right? So here matched. The reference patterns are represented by sticks. The position intensity of the reference stick should be matched. It's almost matched. So it can be accepted. So it can say this is so and so substance. And K-alpha1 and K-alpha2 pick doublets rather than just a single peak. Yeah. Suppose we expect a single peak only, but so because of the technology issues, we'll be having the K-alpha2 peak also. The K-alpha2 peak almost half of the K-alpha1 amplitude, right? Right. So you can see from these images, you see here the angle is 26 something, so, but here 54 something and 55 something. See, what's the major difference in the K alpha 2 doublet? So K alpha 2 here it is simply the peak is not much visible. It's a small bend only, but whereas here there is a gap between the main peak and the K alpha 2 peak. So what we can understand is as long as the angle is increasing, the K alpha 2 peaks are visible. Of course, this is not required because this the red line only the peak as per the reference, but this might be the latest machine. This might be removed. The K alpha 1, K alpha 2 peaks, the blades are further apart at higher angles. At higher angles, it is further apart. The K alpha 1 peaks always be twice the intensity of the K alpha 2. Right? At low angle, 2 theta, you might not observe a distinct second peak. The second peak is not very distinct here. So, right. So this is about K alpha 2. Right. The experimental data should contain all major peaks listed in the reference pattern. Yeah. So everything should have this measured one should have the reference peaks, right? All reference peaks should have, right? So if see here, so one peak is missed here. See, this is what major peak. If the major peak is missed here, they cannot be accepted. But whereas here there are 3 peaks, but it's a minor peaks, but it is also not there. But however, it can be accepted because these are all minor peaks, and so because of some error noise, it can be it may not be seen here. But these things can be accepted, but this cannot be accepted. Right. So these are the some of the ways to interpret the XRD spectra and the applications of the XRD. The XRD diffractions can be used to analyze, we already told the microstructure of the single crystal or powder sample or polycrystal. As a powder means it consists of a number of ingredients which is a polycrystalline. But if it is a single crystal, diffractometer used to find out the molecular structure of the novel compounds. That you see. But if comes to the polycrystalline or powder sample, the fingerprint identification of various solid materials, it is used for the identifications of the various solid materials present in the particular powder. Right? So in powder or polycrystalline diffractions, it is important to have a sample with a smooth or plane surface. Yeah. So if it is a powder sample, it should have a smooth plane surfaces. First, initially, it has to be grounded, and the particle size is supposed to be 0.002 mm to 0.005 mm cross section. Right? It has to be grinded with the help of some mechanical milling and other thing. So it has to be grinded then, and the homogeneous mixer, the ideal sample, it should have a homogeneous mixer, and the crystallites are randomly distributed. The sample is pressed into a sample holder so that we have a smooth flat surface. See here, it's supposed to be a homogeneous, but the distribution is supposed to be a random, right? So we can get the uniform diffraction pattern. So all the molecules can be available for all inclinations so that you can get the uniform spectrum. See, yeah. So this already we discussed a single crystal specimen diffractometer. So it produces only one family of peaks in the diffraction pattern. Yeah. So this we discussed. So if a polycrystalline sample should contain thousands of crystallites, therefore all possible diffraction peaks should be observed. So all possible diffractions, right? See here, if it is a single, there is no issue. It's only it's one pattern, right? So because it's a unique pattern, but if it is a polycrystalline, it's a possible, all possible probabilities has to be done, all possible angles it has to be taken. For every set of planes, there will be a small percentage of crystallites that are properly oriented to diffract. The basic assumptions of the product of fractions are that for every set of planes, there is an equal number of crystallites that will diffract, and there is a statistically relevant number of crystallites, not just one or two. Yeah, that's why we said it's supposed to be a random distribution so that the equal number of crystallites that will diffract in all the cases, right? Right. So phase identification. See here. So anodized, brookite, and rutile, right? See, the mix has these three phases of TiO2. Though these three phases are TiO2, it has given you the peaks. These red peaks mean for rutile, and blue is for brookite, and so on. The green for this anodized. So from these peaks, you can understand the phase identification of the particular sample. The diffraction pattern of every phase is unique. See, if 30° 2 theta and it has so and so peak, then it can be identified that it's supposed to be TiO2 anodized. It's a different phase of the same chemical compound can be identified. Right. So by accurately measuring peak positions over a long range of 2 theta, we can determine the unit cell lattice parameters. So the phase is inverse sample. So by accurately measuring the peak positions over a long range of 2 theta, it's supposed to be a long range of 2 theta, you can get the unit cell parameters, so alpha, beta, gamma, and ABC value. So alloying and substitutional doping, the temperature and pressures can create change in the lattice parameters that you may want to quantify. If you want to quantify, suppose after applying some pressure, after applying some temperature, after doping something, after alloying something, so what changes in the phase, what changes in the lattice parameters, whether the lattice structure has changed or not, whether the orientation alpha, beta, gamma has changed or not, whether ABC value has changed or not. Those things, if you want to study, you can study with the help of XRD after doing so and so applications, right? Use many peaks over long range of 2 theta so that you can identify and correct the systematic errors such as the specimen displacement and the zero shift, right? So it's take the maximum possible 2 theta so that we can get the error-free results. So measure peak positions with the peak search algorithm or profile matching. Once if you observe this peak, that has to be searched, that has to be search and match with the referenced by profile matching fitting techniques or search algorithm. So many software available to search and match. Right. Next, the crystal size also can be calculated. So these are the applications. What we discussed so far are the application. The crystallite smaller than 120 nanometer create broadening of diffraction peaks. Diffraction peaks broadening. What is it? Is see in the red line. You know this is what broadening of peak. The broadening of peak is depends upon the molecule, the crystal size. The size is less than 120 nanometer. It creates broadening of diffraction peaks. This broadening, peak broadening, can be used to quantify the average crystallite size of nanoparticles using Zerar formula. The crystallite structure, the size of the crystallite structure, right, of nanoparticles. This is not nanoparticle size, so please try to understand. This is the crystallite size of the nanoparticles that can be measured. So with the help of Zerar formula, B is equal to K alpha divided by L cos theta, where alpha is the alpha not alpha, lambda. Lambda is the length, L is the what the thickening. What is it? What it is, right? This broadening of peaks. This distance here, the distance of broadening of the peak. Right? So with that, using this formula, you can find out the crystal size calculation. Next one is the database, right? These things we discussed already. So with the PDF, it's available. So with the JCPDS, so you can refer the data and you can identify the material. And coming to the diffractometer, what is a diffractometer? So diffraction, the device which utilizes the XRD diffraction principle and gives and able to observe, able to read the diffraction pattern is called diffractometer. It consists of X-ray tube, the source of X-rays, incident beam optics, and the goniometer. Goniometer is the platform that holds and moves the sample, optics detector and our tube, the sample and sample holders, receiving side optics and detectors. So it accounts the number of X-rays scattered by the sample. So these are all includes to form the diffractometer. See, so that is what diffractometer, but we are talking about only goniometer. See here, the goniometer is what, which includes the X-ray tube, sample or sample holder, and detector. This is what goniometer, the part of the diffractometer. This is what we call as a goniometer, right? See, so we are much interested in the study of XRD spectra. So how to interpret, how to study, that is very much important than the physical component available in the XRD instrument, right? Right. See here, there are theta theta and theta 2 theta goniometer. What is the theta theta goniometer? In the theta theta goniometer, the sample is fixed. The sample is fixed in the sample holder, whereas the tube and detectors are moving with in step of alpha. Sorry, in theta. You can take the theta, right? See, if it is theta, and this also will be moving with theta. So tube and detector will move with the same velocity theta. That's what theta theta goniometer. In theta 2 theta goniometer, the tube is fixed. In theta 2 theta goniometer, tube is fixed, where sample and detector can move. The sample is moving with the velocity theta, whereas the detector can move with the velocity of 2 theta. This is what theta 2 theta goniometer. Right? So I repeat it again, the theta theta goniometer, sample is fixed. The tubes and detectors are moving with the theta. Whereas in theta 2 theta goniometer, the tube is, X-ray tube is fixed. Whereas the sample and detector are moving. The sample is moving with the theta, whereas the detector is moving with the 2 theta. Okay, so this is about the brief about XRD. I hope it will be useful to you. And so before going to the next one, I would like to play a video, right, which will